Sup, Kim peeps? What in the heck are we gonna do in this vid? Always a great question. We are going to use a set of initial concentrations or partial pressures, the equilibrium constant, and stoichiometric relationships to quantitatively determine the concentrations or partial pressures at equilibrium. So, two things. One, we are going to predict the concentrations at equilibrium when given the initial concentrations and our equilibrium constant K. Two, we are going to create and use ice, baby, tables for determining concentration values that are consistent with the stoichiometry for a given reaction. Alright, so many equilibrium calculations are solved using what we call the ice table method as a way to clearly track what happens as a reaction establishes equilibrium. Ice tables. I stands for the initial concentrations or pressures for each species in the reaction mixture. C represents the change in concentrations or pressures for each species as the system moves towards equilibrium. And E represents the equilibrium concentrations or pressures of each species once the system is in the state of equilibrium. Ice tables. Few things to keep in mind when you create ice tables. One, express all quantities in terms of concentration, moles per liter. Two, keep in mind that the change in each quantity must be in agreement with the reaction stoichiometry. We often represent that by the variable x. And you need to think about what is formed and what is consumed when determining whether the sign of those changes will be positive or negative. And then three, keep in mind that some students find it helpful to call these rice tables to remember to include the balanced reaction. I prefer ice tables just because I like the song. Ice tables. All right, so let's take a look at an example to better understand how ice tables are going to be used in class. Consider the following reaction. Boom! A reaction mixture at 780 degrees Celsius initially contains 0.500 molar carbon monoxide and 1.00 molar hydrogen. At equilibrium, the carbon monoxide concentration is found to be 0.15 molar. What is the value of the equilibrium constant? Write your equation, set up your ice table. Ice tables. Step 1. Set up known initial concentrations and equilibrium concentrations. We're told the initial concentrations of carbon monoxide and hydrogen, and we can assume that, because those are the only concentrations we are given, that the concentrations of the other species, in this case the methanol, is 0. And we're told the equilibrium concentration of CO is 0.15. So important to note that we've had a decrease from our initial to equilibrium concentration for our carbon monoxide, which indicates the reaction is shifting to the right to establish equilibrium. Step 2. Since we know initial and equilibrium concentrations, let's calculate the change in concentration that occurs. We must have had a decrease of 0.35 molar concentration to get from 0.5 to 0.15. Step 3. We're going to use the stoichiometric relationships in the balanced chemical equation to determine the change in concentration for all the other reactants and products. So if I know that my carbon monoxide has decreased by a concentration of 0.35 molar, I know that my hydrogen has decreased by a concentration of 0.70 molar, and the concentration of my methanol has increased by a concentration of 0.35 molar. Again, carefully examine the stoichiometry to understand why those changes are written as they are. Step 4. Sum each column to determine the equilibrium concentrations. Easy. 1 minus 0.7, 0.3. 0 plus 0.35, 0.35. Step 5. Solve for the equilibrium constant using the equilibrium concentrations that we just determined in the previous step. Don't forget, your equilibrium constant expression is products over reactants. Always write this out. Even though you're not asked for it, always write it out. Plug in our equilibrium concentration values, then just bust out your calculator and solve. 0.35. Divided by parentheses, 0.15, close parentheses, new parentheses, 0.30, close parentheses, squared, close parentheses, enter. And that's how we get 26. Boom.